Yeah. Mark, where are you at? You probably know.
If you have a SDR, you can actually use a little bit of Euler's relation, because you can actually do an asymmetrical amplitude modulation by superimposing you actually have to. The problem with AM modulation is that it's the convolution of your input signal and your carrier in the frequency domain, and it's always symmetrical. So the only way you can get around it is if you had a complex IQ modulator. So if you had an SDR, you might be able to do it by slightly adding another carrier around the center of your AM carrier, but it's actually single sideband and really wide. That's how you would do it. KC3FKR from the academic sphere.
Yeah, that's interesting. A guy that I know built something like that, analog, with like double balance mixers, and I think the IQ signals are pretty much just audio. You only need one for AM, obviously, and then there's two for sideband, and then one's reversed in phase, some crap like that. But he built an IQ modulated exciter out of just like double balance mixers and oscillators and stuff.
Yeah, it's not too hold on. It's not too crazy. All it really is two balanced mixers, and the carrier that you're using to upconvert is 90-degree phase shifted on one, and that gives you your in-phase and quadrature signals, which if you actually plot them with respect to time on a XY axis, form the unit circle if you're doing amplitude modulation. So in AM, you vary both simultaneously in phase. In single sideband, you phase shift one of them by a certain amount. It's usually 90 degrees, and then either rotate one signal 180 degrees out of phase, subtract or add if you want to do upper or lower sideband. And that's called a Hilbert transform, and that's the entire basis behind single sideband. That's how the phasing rigs worked back in the 50s and 60s. KC3FKR.
I heard of a couple ways to do it, like phasing method, filter method, and the Weaver method, which was with 4 mixers. I get like two in front of 2.
Yeah, that's almost like you're making a BFO within your receiver. It's like an emulated BFO. So it's similar to how the Weaver method I'm referring to.
Yeah, I was just starting to wrap my head around it. I was considering building an IQ modulated exciter just because I think it's so cool. I mean, at least the guy I saw who did it, he was doing like crazy stuff like modulating square waves on AM and with no harmonic stuff, and like just stuff you can't do with most transmitters. I mean, it was making like perfect AM. And then, you know, you could do any mode with it. Sideband, independent sideband, for stereo, like all kinds of stuff. It was just really cool. I want to get a little more into it. It sounds like you kind of know the ropes, man.
Well, needless to say, I actually started an SDR project a little while ago and have been piecing away at it. And it's just a receiver, so I know the processing that goes forward from receiving transmits the exact opposite. And I'm also taking a digital communications class where we discussed it's called higher order modulation, where you use the amplitude and phase component of a signal to represent any arbitrary waveform. So you could do anything you want, really. You could do spread spectrum, you could do digital television, you could the limiting factor in your system is going to be the hold on a second.
This space for rent.
What?
On the transmitter, it was creeping up in plate current. So yeah, the limiting factor in your bandwidth on AM, if you're using an SDR, is either the pre-filtering in the processing, or it's the bandwidth of your digital analog converters. So also your bandwidth of the double balance mixer that you're using. So also keep in mind for correct IQ comparison, your INQ signal must have almost no DC offset, so you have to have really good DC blocking there. Otherwise, you get a carrier leakage component there. So SDRs are pretty crazy when you look at them on the surface, but when you actually delve into the math and start looking at everything, it actually starts to make sense. If you've done any simple trigonometry, the math pops right out. KC3FKR, Newark, Delaware.
Yeah, the math is one thing. I'm just trying to understand, you know, IQ signals and how, you know, you'd make a receiver, an IQ receiver, an IQ modulator. That's just where I'm starting. The math I'm not so good with, but just wrapping my head around this stuff is enough for now. Interesting conversation, though. You're the first person I've been able to talk to about this. Just one more thing from my own understanding. Basically, like, if you were to make a transmit, you know, an IQ modulated, you know, the transmit side, in other words, versus the receive, it's all done with double balance mixers. And for transmit, you basically just replace the local oscillator from the receiver with RF. Is that, like, correct?
So your question is, if you want to do transmit, you replace the local oscillator with the carrier that you want to transmit on? Is that what you're saying?
Yeah, exactly.
So with an SDR, a lot of them that you buy that are cheap are direct conversion. So they have an IF, which is derived from a carrier, right? So you have whatever if you're on HD SDR, you can actually see it, but there's an LO selection, and then there's a tune selection. So a lot of times the LO stays fixed in the center of the band, and then what you do is you generate the offset that you want in frequency by upconverting the speech information in software, and you can do that with the Weaver method. So you just tune the internal software defined local oscillator to mix your voice data up to a high frequency in the middle of your IF passband, and then you can retune your signal without retuning the LO, which is kind of the weird part about it. Also, you can receive negative frequencies with Quadrature. So a lot of people say, well, what's a negative frequency? Well, it's the complex conjugate, meaning there's unit circles spinning in reverse. You can think of the I and Q signals as a helix spinning towards you in time, but what basically happens when you go into negative frequency is the helix starts rotating in the other direction. So you can get positive and negative frequencies relative to your local oscillator that way. So when you go into transmit, all it does is swaps out the incoming RF to the balanced modulators or mixers in the IQ section, swaps out the antenna for the IF digital analog converters, and then the output of that balanced mixer stage in Quadrature, when it's summed back together, ends up being your transmit signal, and it's already been upconverted due to the fact that it's been mixed. So really simple. It takes barely any parts to do. So if you have a couple SBL01, I forget the name of the company, but mini circuits, they make SBL01s, I think, in the name of the mixers. You can make your own little Quadrature mixer there, and then you can just pump audio in phase into INQ with your carrier, and you're going to get DC to light AM out of it. So what you said was mostly true. You just flip the LO, you flip the direction of the signal path, so you go backwards through the mixer to get back up to RF. KC3FKR.
Well, good night, gentlemen. Ooh, one sec. Okay. Well, I did have the antenna tuned, but it started arcing. Okay. Mighty fine junk at its best. We're just barely starting to study to become an ED, so this is out of my league, so good night. And yeah. Now I gotta figure out why that was arcing, because that should not be happening in a 1.5 kilowatt MFJ roller inductor tuner. 73 W4IPC. Click.
Dear. Later. Yeah, this is KA2PVT. I think me and Billy doubled it with KC3FKR. You're at the university in Delaware, right?
I'm not at the university. I'm at my house, but I'm a student there. I'm a sophomore electrical engineering student, and I've had a little bit more time in the field than I've been in university, so I've actually been working with a RF systems engineering company that does millimeter wave radar imaging, so have a little bit of a leg up on a lot of the common classes, and this stuff just fascinates me. I just read and read and read, and it just sinks right in because I'm using it in the real world. KC3FKR.
Yeah, okay, real good. Yeah, this is Eric. I'm in Newark, New Jersey. I think the university's in Newark, Delaware. Newark, Delaware, as you pronounce it down there. Okay, real good. Well, hey, this is an education. I mean, yeah, I'm an ET from the 70s from DeVry, so I just retired, and you know, a lot of this stuff sounds new to me, but then as I listen to it, yeah, it does make a lot of sense. So, real good. Okay, and you know, yeah, in the digital realm, you can do a lot of stuff that you couldn't do analog.
Yep, that's the beauty of it. You just got to be real careful when you do digital things, and one of the biggest problems with doing things digitally in a lot of radio applications is imaging or images that you get in your receiver due to aliasing. So you have to have really good filtering, and you have to take care that your quantization error, which is a thing based off of your bit depth in your SDR. So you see, like on Flex, they have like a 24-bit ADC and DAC. And then the RTL SDR dongles, they have 8 bits. So with more bits inherently becomes a lower noise floor. But when you have more, if you have less data points to sample off of, then your inherent digital noise floor comes up. And also, if you don't filter it right, you get all sorts of problems with recreating the original spectrum that you're looking for. If your sample rate's too low, you're going to get overlap in your spectrum, and it's going to distort, and you're going to have the characteristic sync function response out on the edges of things, and it's just not good sometimes. So you just got to keep all your eggs in one basket and make sure you count them every 5 seconds. KC3FKR. Yeah, and Newark, Delaware. Hello there, Eric.
The Nyquist limit, too, gets you every time. Aliasing.
Yeah, the Nyquist limit, that's a big one. Usually, if you want to do any form of software-defined radio, your band of interest has to be at least 1/10 wide of the sample rate, at least. You want to oversample by 10 most of the time. And that's why you see digital oscilloscopes rated for 100 megahertz that sample at 2 gigasamples per second.
Okay, real good. Yeah, what's the name down there? And also the other question: were you involved with the AM station that you guys are running at the university? This is like a couple of months back, but I don't know, because the call sounds familiar. So you were probably the same person that was running the station at the school.
Yeah, that was me. Bought the Collins 20V3 and brought it over there. Yeah, unfortunately that's gone kaput, not only because of the coronavirus, but because politically it was real difficult to get space to do that stuff in, so kind of ran out of headroom. KC3FKR, and the name here is Daniel. Delta Alpha November, India Echo Lima. Also, holy cow. Billy, you're literally 50 over 9 here.
Yeah, look at that. Running 24-bit audio. That's 144 dB of dynamic range. W2BTK.
That's a lot of dynamic range.
Man, what's the spurious free dynamic range? That's a different thing than your linear dynamic range, so you got to do a two-tone test.
See, I went to college and learned that, and I don't know what you're talking about. But then again, I went to music school, so I learned all about digital stuff in the context of audio, and only in audio. And I think they did that for reasons why we wouldn't get confused, because, you know, I wasn't sitting in a room of future electrical engineers. I was sitting in a room full of musicians who had their head wrapped around this stuff a little bit.
Whiskey, man, whiskey.
Hey, you want to talk about dynamic range? Well, in the audio, well, the digital realm. You know, a lot of these recording engineers, you know, when like CDs first came out in the 80s, they were really harping on, you know, 110, 120 dB of dynamic range. Well, when the CDs came out back then, they were utilizing, you know, that aspect of the goodness of a, you know, new digital audio. Nowadays, you get a CD, it might have 40 dB of dynamic range, and it's just criminal what they've been doing, you know, running so much compression and, you know, not utilizing the wealth of dynamic range. But anyway, I listen to a lot of jazz and classical music, and that's when you can really tell the difference.
Yeah, well, for the most part, I mean, especially after the 90s loudness wars, you know, you're a music guy. It's all audio sausage, man. You look at the waveform of any song, and it's already like a square wave, and then they play it over the radio, and you know what, like, you know, all this processing does to stuff, and it's crazy, man. But yeah, like older music, you used to look at a waveform of, like, you know, like an early 80s or something, like electronic track. Those snare drums, that was a big transient, and it was much louder than the, you know, the average level of the music, and it popped. And you know, people listened to stuff with dynamic range back then. Now, you know, MP3s, headphones, ear pods, all that crap. It's like audio sausage just to get it to sound full on anything. Nobody knows about dynamic range anymore, but it's really cool. And you're totally right. Classical music has probably the most dynamic range out of anything you could want to listen to. But, you know, again, it's like 24-bit audio. You have that ability, but it's all just using 24 bits all the time. So what?
Yeah, you have the benefit to actually look into all of that resolution, and the CD format still supports it. It's not like the discs have changed, but I have a feeling a lot of it's just mastered in 16-bit on some SoundCloud rapper's desktop computer.
Yeah. Well, not only that, it's just that, yeah, it's the same dynamic range is available, but it's these new school, you know, engineers that lay the tracks down. They don't utilize it anymore. You know, I was, you know, my career, I was a consumer electronics tech. So, you know, back then I did component level troubleshooting and all of that. So when the CDs came out, you know, I worked on the first CD players that hit the market, and they were horrendous. But anyway, it was a new format. And I have CDs from the 80s that were, you know, not remastered from, you know, analog tapes and all of that. And they sounded better back, you know, from the older ones than they do now. I mean, compression, it gives me a headache, you know, and I'm trying to listen to music, you know, when there's too much compression in it, it just gives me a headache. I like it nice and open, where a whisper sounds like a whisper and a crescendo sounds like a crescendo. But you're an older guy, so, you know, I don't know, the newer, you know, the newer engineers out here, I don't know if they respect that anymore. That's all I'm saying.
You know what it is? Like, just from seeing the trend, it's like, if you don't do that, then the next guy's track is just gonna sound louder. It's the same thing on the radio, especially like CBs and stuff, you know. It's just like, who's louder? Like, that's who I want to listen to. Radio stations, you know, they've all been through this, you know. That's why they get little tiny kilowatt stations competing with, you know, big kilowatt stations by running, you know, just some more modulation, some more loudness. And that's it, man. It's like, you could use the dynamic range and stuff, but they're gonna listen to somebody else's track first at a lower volume, and it's all gonna be right up there up front, and yeah, there's no dynamic range. But then your track comes on with tremendous dynamic range, and it just sounds quiet. People are like, well, they get bored or whatever, and it's really sad, but it's true. And it's perfect examples, like, just here on radio, you know, just pay attention to it. W2BTK.
Absolutely, yeah. Well, been there, done that. I grew up listening to AM radio in the 60s and 70s, and yeah, you're absolutely right. But what always drew, you know, the stations that I mostly was drawn to was the ones that had some dynamic range, that weren't screaming at you all the time. So there you go. And anyway, not to jump off of the subject, but that's my little pet peeve. So back to you, Daniel, and I'm a little curious of what you're transmitting on down there. So I just widened my bandwidth out, and you're sitting in the room here with me at the listening post, KA2PVT.
Yeah, KA2PV. Hold on, there we go. KA2PV KC3FKR. Yeah, the transmitter here is a full legal limit plate modulated transmitter. It runs a pair of 813s in the final, standard Class C parallel configuration, and a pair of 813s in the modulator in Class AB, AB1. I've been experimenting with different modulation different bias schemes for this modulator, but putting out about 375 watts carrier here, and this thing will do 100%, so I guess that's legal limit. And the antenna is a flat-top dipole fed with open wire feed line, made of 12-gauge speaker wire. I spent like $12 on that feed line, and that thing's been up for 3 years now, so no complaints with that. And the let's see, the audio chain here is an Audio-Technica BP40 broadcast microphone. That feeds a McMartin B801 mono console from 1961, all transistors, which then feeds a Symmetrics 528 voice processor, and then a graphic EQ out to the transmitter. So really old school analog setup here, but I was just doing some burn-in tests on a new exciter I designed for this transmitter, and what I was doing was I was playing some music through the audio chain, and man, I cannot distinguish it from like big shortwave stations like WTWW and all that, man. This thing has excellent sound quality, and the modulation transformer is a BC610 modulation transformer, so no Heising reactor, nothing. It just sounds wide open. That being said, I have another modulation transformer from a Collins 20V3, the one that's at the university. I have a spare, so I have to get that working. Stand by, I'm having a phone call. You guys carry on for a second.
Daniel, well, I got to tell you,